Welcome to Daily AI and Machine Learning Lessons. I'm Blake.
And I'm Jude.
Today, we're taking a deep dive into an area of machine learning that I find genuinely fascinating. It's all about how AI systems manage to learn effectively, even when we don't, hand feed them perfect, fully labeled data sets.
Hmm.
It's about getting incredibly smart with very limited labels, this powerful concept known as semi-supervised learning. And, this isn't just some academic theory. It's a constant pressing challenge in the real world of AI deployment.
That's absolutely right. So our mission for you today is to unpack exactly what semi-supervised learning, or SSL, is, how it works its magic, and crucially, why it's becoming so incredibly powerful for modern AI. It makes advanced systems far more practical, more accessible than ever before.
Yeah, it sounds like a shortcut almost.
It really is. Think of it as a shortcut to becoming truly well-informed without drowning in that whole data labeling process.
Okay, so let's start with the elephant in the room, right? The
Yeah.
core challenge that makes SSL so necessary, what we call the labeled data dilemma. Think about it. Deep learning models, the kind that power so much of the AI we see today, they demand absolutely vast amounts of training examples,
Hmm.
just enormous amounts.
Huge amounts.
And when you look at foundational data sets like, say, ImageNet, which fueled so much progress in computer vision, I mean, the sheer human effort required to hand label millions upon millions of images is just staggering. It's unbelievably expensive and so time consuming.
Exactly. And here's the kicker. While labeled data is like gold dust, really precious and hard to get, vast quantities of unlabeled data are, well, they're quite literally everywhere.
Right, like all the images scraped from the web.
Exactly. Images crawled from the web, or billions of text documents online, or even raw sensor data from IoT devices. They're just sitting there, unlabeled, waiting to be used.
Yeah.
And this is where semi-supervised learning steps in as this uh, really ingenious, almost revolutionary approach to tackle that imbalance.
So, if I'm getting this right, it's essentially about getting the best of both worlds. SSL combines that small, precious amount of human-labeled data with that much larger, readily available pool of unlabeled data to train models.
Precisely.
It feels a bit like using a few expertly guided trails to kind of navigate an entire uncharted forest.
That's a great analogy. And the core objective of SSL isn't just to use unlabeled data. It's to enable a model to perform significantly better than if you had trained it using only the limited labeled data you had.
Ah, okay, so it boosts the value of the labels you do have.
Exactly. It maximizes the value of every single label, allowing the model to extrapolate and learn from that vast ocean of unseen information. It really is that shortcut to creating well-informed systems without the prohibitive cost and time of traditional labeling.
Okay, that makes a lot of sense. We've got this sea of unlabeled data, a tiny island of labeled data, and SSL helps us bridge that gap. So let's dive into the core mechanisms then. How does it actually do this? Let's unpack the three sort of foundational concepts that typically come together to achieve semi-supervised learning. These are the fundamental building blocks, really, that empower models to learn from less.
Okay, the first one, and arguably one of the most powerful, is consistency regularization.
Consistency regularization. Okay.
What this technique does is enforce a critical, almost intuitive rule. If you make realistic, small changes to an input data point, the model's output prediction for that point should not change significantly.
So, like, if I see a picture of a cat and then you show me the same picture slightly rotated, I still see a cat.
Exactly. You're consistent. A machine learning model should be too. It should give consistent outputs for an input and its slightly altered versions. We humans are quite robust to these small perturbations, aren't we? Adding a bit of noise to an image is often imperceptible to us, and the idea is a model should have that same robustness.
That makes perfect sense conceptually. But how do we actually achieve this consistency in a model? Like, what kinds of realistic perturbations are we talking about?
Well, mechanically, it's typically done by minimizing the difference between the model's prediction on the original input and its prediction on a perturbed version of that input.
Okay.
So in computer vision, for images, you'd think about common sense manipulations. Things like flipping an image horizontally, rotating it slightly, maybe cropping it differently or mirroring it, even adding tiny, almost imperceptible noise to pixel values can work.
Things that don't change what the image is.
Precisely. These are transformations that preserve the core identity of the image. The dog is still a dog, just seen from a slightly different angle or with a minor blur.
Gotcha. And what about in language? Text doesn't really flip or rotate in the same way. How do you perturb text realistically without just scrambling the meaning?
Ah, that's a great question, and it's where some real ingenuity comes in. The most popular technique in natural language processing is called back translation.
Back translation.
Yeah. You take an input sentence, say in English, you translate it into a different language, maybe French or German, doesn't really matter, and then you immediately translate it back to the original language, English.
Oh, interesting.
What happens is this process creates a new input sentence that has the same semantic meaning. It says the same thing, but often with different phrasing, different word choices, maybe a slightly different sentence structure. It's a fantastic way to generate a perturbed variant that's still fundamentally the same core idea.
That's brilliant. So you get variation without losing the essence. Why is this consistency regularization such a big deal then? What's the kind of deep insight here for our models?
Well, the insight is that it's a really powerful way of leveraging all that unlabeled data to help the model discover what we call a smooth manifold.
A smooth manifold. Okay, unpack that a bit.
Imagine data points aren't just scattered dots, but more like beads arranged on a piece of silk fabric. A smooth manifold is that underlying fabric itself, the inherent continuous shape or structure of the data. Consistency regularization helps the model sort of feel this underlying structure, even for the unlabeled points.
Ah, I see.
It helps it understand that similar data points, even with slight variations, should naturally cluster together. It forces the model to learn the inherent, robust features that truly define a class, rather than getting distracted by superficial differences or noise.
Makes sense. Okay, concept number 2, entropy minimization. This one sounds a bit more abstract, maybe, but I know it's incredibly important. What does it mean for a model to minimize entropy?
Yeah, it sounds technical, but the core idea is pretty straightforward. In simple terms, minimizing entropy encourages the model to be highly confident in its predictions,
Highly confident.
especially for that vast pool of unlabeled data where, remember, we don't actually know the true answer. For a classification task, it essentially wants the model's prediction for one specific class to be very close to 1 how, meaning 100% sure, and for all the other classes to be very close to 0. It discourages ambiguity or wishy-washy predictions.
So it's like pushing the model to make up its mind, like a confident student who doesn't just say, maybe. Why is that so crucial, especially when dealing with unlabeled data where it could be unsure?
Exactly. It's about pushing the model towards decisive classifications. Minimizing entropy discourages the model's decision boundary, the line it draws between classes from passing too close to the actual data points.
Right.
Think of it like building a fence to separate, I don't know, dogs and cats in photos. If your fence runs right through a cluster of photos, the model might be uncertain about which side some photos belong on. Entropy minimization pushes that fence into the empty space between the clusters.
Ah, so it forces clearer separation.
Right. It encourages the model to build really clear, decisive boundaries between classes, creating more defined regions in its internal representation for each category. And this is really important because it makes the model's pseudo-labels more reliable. It brings us perfectly to our third concept.
Ah, yes, pseudo-labeling. This one, on the surface, it seems almost deceptively simple, yet I know it's incredibly effective. Walk us through how a model starts to learn from its own predictions.
Yeah, pseudo-labeling is perhaps the most intuitive approach to SSL. It works in a few steps.
Right.
First, you take your small initial labeled data set, the gold dust we talked about, and you train a model on it. This gives you a foundational classifier. Maybe not perfect, but a starting point.
Okay, step 1, train unlabeled data.
Step 2, you then use this partially trained model to make predictions on the entire large pool of unlabeled data. All those images or text you didn't have labels for.
Got it. Predict on everything else.
Now, here's the crucial step, step 3. The system selects only those unlabeled examples where its prediction is highly confident. Say, above a certain threshold, maybe it has to be 90% or 95% sure about its prediction.
Right, filter for high confidence, and these highly confident predictions become what?
These confident predictions are then treated as pseudo-labels. They're not human verified, obviously, but the model is confident enough in them that we treat them as if they were true labels.
Okay.
And then step 4, this new expanded data set, which is your original human labeled data, plus all this new pseudo-labeled data, is then used to retrain the model.
Retrain with the pseudo-labels added in.
Exactly, and you can even do this iteratively. Retrain, generate new pseudo-labels with the hopefully improved model, retrain again, creating this powerful feedback loop.
It's fascinating because it feels a bit like, pulling yourself up by your own bootstraps. If the model starts with key mistakes, couldn't it just amplify those mistakes by confidently pseudo-labeling something incorrectly and then training on its own errors? How do we know this actually works and isn't just like a house of cards ready to fall?
That's an excellent, excellent question. And it gets right to the heart of why this isn't just a clever trick. It's where the theoretical underpinnings of self-training, which pseudo-labeling is a core part of, really shine. There's strong mathematical and theoretical analysis explaining why this leads to provable improvements, not just reinforcing errors.
Okay, so there's some solid theory behind it. Yeah.
Absolutely. The secret sauce, or a key ingredient anyway, lies in something we mentioned earlier: input consistency regularization during that retraining phase.
Ah, the first concept we talked about.
Exactly. Using consistency regularization alongside pseudo-labeling is critical. Without it, the model might indeed just reinforce its own biases or errors and not actually improve its decision boundaries effectively. This regularization encourages consistent predictions on neighboring examples, which turns out to be key.
So it's not just about being confident, but being confident consistently across similar inputs. But how do we define neighboring examples, especially when we're talking about potentially complex, high-dimensional data like images or text?
That's where it gets really interesting, and we need to introduce a concept called the augmentation graph.
Augmentation graph, okay.
Imagine a conceptual graph, like a giant network. Each data point could be an image, a sentence, whatever's a vertex, a node in this network. And edges connect semantically similar data points.
So an image and its flipped version would be connected.
Exactly. Or an image and a slightly rotated version, or a sentence and its back-translated version. These are neighbors in the augmentation graph because the augmentation, flipping, rotating, back-translating, connects them.
Okay, I can picture that.
Now, what's truly fascinating and important here is that this augmentation graph isn't just defined on the limited training set we have. Theoretically, it's defined on the entire population of data that could possibly exist.
The whole universe of potential data.
Sort of, yes. The complete distribution. This distinction is crucial because properties like connectivity, how well points are linked, are much more realistic and stable when you consider the vast, complete population, rather than just our small sample.
Okay, so we're thinking about this theoretical ideal network of all possible data and its connections. How does this relate back to why self-training actually works and improves the model?
Well, the theoretical analysis shows that for self-training to achieve provable accuracy improvements, two core assumptions about this underlying augmentation graph generally need to hold true.
All right, what are they?
The first is expansion within classes. This basically means the graph has good connectivity within the same class.
Good connectivity within classes means...
Meaning, if you take a set of data points belonging to the same true class, say, all dog images, the neighborhood of that set in the graph must expand significantly to include more examples from that same dog class. Think of it like information spreading easily among all the dogs. A larger expansion factor means better connectivity, allowing knowledge to propagate effectively within a class.
Okay, so things of the same type are well connected. What's the second assumption?
The second is separation between classes. This ensures that there's clear separation between different true classes. In the graph, there should be very few edges connecting data points from different classes, so few connections between dog images and cat images, for example.
Right, the boundary should be clear.
Exactly. It means true decision boundaries tend to pass through low-density regions, the gaps between different classes in this graph structure.
Okay, so if the data naturally has these two properties, good connections within a class, and clear separation between classes, that's when the magic happens. You mentioned a denoising effect. Tell me more about this. It sounds like the model can actually correct its own mistakes.
Precisely. That's the core insight. Under these two assumptions, expansion within classes and separation between classes, self-training provably leads to a classifier that is more accurate than the original model that just did the initial pseudo-labeling.
How's it denoise?
Think about it this way. Let's say your initial pseudo-labeler makes a mistake. It labels a particular dog image as a cat. But if that mislabeled dog image has many correctly pseudo-labeled dog neighbors in the augmentation graph, because of good within class expansion,
Okay.
then the input consistency regularization term kicks in during retraining. It encourages the model to predict the same label for all these connected neighbors. The signal from the many correct dog neighbors essentially overrides or denoises the single incorrect cat pseudo-label on that one image.
It's like peer pressure for labels. The correct labels gang up on the incorrect one.
That's a great way to put it. The correctly pseudo-labeled examples effectively correct the incorrectly pseudo-labeled ones through this consistency pressure across the graph connections.
That's amazing. And I guess this is why using stronger data augmentations, more varied ways of perturbing the data, is often so effective in practice because it creates more connections, increases that expansion coefficient, making the denoising process even more powerful.
You've got it exactly. Stronger augmentations build a more robust and densely interconnected neighborhood for this knowledge propagation and denoising to happen. It truly becomes a self-improving feedback loop.
And this whole theoretical analysis, does it hold up for the complex models we use today, like deep neural networks?
Yes, that's what's really significant. This analysis provides a robust explanation for the empirical success we see with deep neural networks in semi-supervised settings. It highlights something quite profound. Deep learning models, unlike some older traditional methods, seem able to leverage these properties of the population distribution, that huge theoretical augmentation graph, even when they're only trained on finite samples. They implicitly extrapolate local consistency to a more global understanding.
That's a really deep insight. So we have the theory, we understand why it works, which is fantastic. But what does all this look like in the practical world with actual machine learning models that people are building and using?
Right, moving from theory to practice.
Yeah.
Well, one of the early, quite impactful approaches that specifically implemented consistency regularization was the A model, the pi model.
The pi model, okay.
It essentially encouraged consistent model output by running the same input through the model twice, but each time with different random perturbations applied, like dropout acting differently. Then it compared the two outputs and pushed them to be similar.
So forcing consistency on the fly.
Exactly. It had a big impact, but it also had drawbacks. Training was computationally expensive because every single input had to be passed through the model twice in each step. And the consistency target could be a bit noisy since it was just based on one other perturbed prediction at that moment.
Makes sense. So expensive and maybe a bit unstable. How did the field evolve from there?
Well, to address those efficiency and stability issues, temporal ensembling emerged as an evolution of the A model. It still focused squarely on consistency regularization, but it did it in a much more efficient way.
How so?
Instead of comparing two predictions from the same training epoch, it compared the current model's prediction on an input with a weighted average of its predictions on the very same input from previous epochs.
So it's like comparing the current prediction to a smoothed out history of predictions for that input.
Precisely. It builds a more stable ensemble prediction over time to use as the consistency target. This made training faster, only one forward pass needed per step, and the target itself was smoother and less noisy.
That sounds like a definite improvement. Any downsides?
The main drawback was the need to store these historical ensemble predictions for all the training examples across epochs. For truly massive data sets, that could become quite memory intensive. But it was a significant step forward in making consistency regularization more practical.
And I imagine the field hasn't stopped there, right? It feels like this area moves incredibly fast.
Oh, absolutely not. The field is constantly advancing. More recent, really cutting-edge techniques like mean teacher, unsupervised data augmentation, UDA, fixed match, noisy student, they all build upon these fundamental principles we've discussed: consistency regularization, pseudo-labeling, but they find clever new ways to refine them, combine them, and push the boundaries of what's possible with unlabeled data.
Mean teacher, UDA. What's the gist there?
Well, mean teacher, for instance, kind of refined temporal ensembling. Instead of averaging past predictions, it averages the model weights themselves over time, using an exponential moving average, to create a more stable teacher model. The student model then learns to be consistent with this smoother, more stable teacher. UDA focused on using really advanced, diverse data augmentation strategies specifically designed to improve consistency regularization performance. Each new method finds clever ways to squeeze even more information out of that vast unlabeled pool.
It's incredible how these ideas build on each other. This whole deep dive into semi-supervised learning, it really paints a clear picture of how AI can learn much more efficiently, more robustly, with far less human-labeled data. And for you, the listener, this has direct, really profound implications. Think about reducing the cost and time needed to deploy sophisticated AI systems. It makes AI more accessible, more scalable across different industries.
Exactly. It's helping us tackle complex problems that previously seemed intractable because they would have required impossibly large, hand-curated data sets. Things in medical imaging, natural language understanding, robotics, areas where getting labels is incredibly hard or expensive.
Yeah.
SSL makes AI practical for businesses, researchers, and organizations that maybe couldn't afford the massive labeling effort before.
It truly is a shortcut, then, to getting these highly accurate, well-informed AI systems out into the world.
It really is. And as we wrap up, maybe here's a thought to leave you with. Consider this core idea we explored, a system learning from its own confident predictions, and perhaps more remarkably, correcting its own mistakes through internal consistency, that denoising effect we talked about.
Yeah.
How might this principle apply beyond just machine learning? Could we see similar dynamics in other complex systems? Maybe even how we structure our own learning processes, using consistency and self-correction for greater efficiency. Something to ponder.
That's a fascinating thought, definitely something to mull over.
Mm-hmm.
That's all for now, folks. Please like, share, and subscribe to help fund this channel.